Analysis of variance involved examining the relationship between a categorical explanatory variable and a quantitative response variable. Next, we're going to consider inferences about the relationships between two categorical variables. The statistical test that will answer this question is called the chi-square test of independence. Chi is a Greek letter that looks like a large X, so sometimes you'll see this test denoted with an X squared. For this statistical tool, let's start with a new example. In the early 1970s, a young man challenged an Oklahoma state law that prohibited the sale of 3.2% beer to males under the age of 21, but allowed its sale to females in the same age group. The case was ultimately heard by the U.S. Supreme Court. The main justification provided by Oklahoma for the law was traffic safety. One of the three main pieces of data presented to the court was the result of a random roadside survey that recorded information on gender and whether or not the driver had been drinking alcohol in the previous 2 hours. There were a total of 619 drivers under 20 years of age included in the survey. On the left, you can see what the collected data looked like. And on the right is a two-way table summarizing the observed counts in the roadside survey. Our task is to address whether these results provide evidence of a significant or real, that is, statistically meaningful relationship between gender and drunk driving. Both variables are two-valued categorical variables, and therefore our two-way table of observed counts is a 2x2. The chi-square procedure, however, is not limited to 2x2 situations, but can be used for a larger number of explanatory categories. Reporting appropriate summaries for a two-way table is deciding which of the two categorical variables plays the role of the explanatory variable, and then calculating the conditional percentages separately, that is, the percentages of the response variable for each value of the explanatory variable. In this case, since the explanatory variable is gender, we would calculate the percentages of drivers who did and did not drink alcohol for males and for females separately. Here's the table of the conditional percentages. For the 619 sampled drivers, a larger percentage of males were found to be drunk than females, 16% versus 11.6%. Our data, in other words, provides some evidence that drunk driving is related to gender. However, this in itself is not enough to conclude that such a relationship exists in a larger population of drivers under 20. We need to further investigate the data and decide between the following 2 points of view. That there is no difference in the drunk driving rate between males and females under 20, our null hypothesis, or that there is a difference in the drunk driving rate between males and females under 20, our alternate hypothesis. In other words, is the evidence provided by the roadside survey, 16% versus 11.6%, strong enough to conclude beyond a reasonable doubt that it must be due to a relationship between drunk driving and gender in the population of drivers under 20? Or is the evidence provided by the roadside survey not strong enough to make that conclusion? And could this have happened just by chance, that is, due to sampling variability, and not necessarily because a relationship exists in the population? These are the null and alternate hypotheses for a chi-square test of independence. Generically, here are other ways that the null and alternate hypothesis can be stated for a chi-square test of independence. There is no relationship between the two categorical variables, they are independent, or there is a relationship between the two categorical variables, they are not independent. Algebraically, independence between gender and driving drunk is equivalent to having equal proportions who drank or did not drink for males versus females. In fact, the null and alternate hypothesis could be reformulated as the proportion of male drunk drivers is equal to the proportion of female drunk drivers, or the proportion of male drunk drivers is not equal to the proportion of female drunk drivers. The idea behind the chi-square test of independence, much like the analysis of variance, is to measure how far the data are from what is claimed in the null hypothesis. The further the data are from the null hypothesis, the more evidence the data presents against it. Here, the gender and drunk driving data are represented by the observed counts. To represent the null hypothesis, we're going to calculate another set of counts, the counts that we would expect to see instead of the observed ones if drunk driving and gender were really independent, that is, if the null hypothesis were true. For example, we actually observed 77 males who drove drunk. If drunk driving and gender were indeed independent, if the null hypothesis were true, how many male drunk drivers would we expect to see instead of 77? Similarly, we can ask the same kind of question about and calculate the other three cells in our table. In other words, we will have two sets of counts: the observed counts, that is the data, and the expected counts, if the null hypothesis were true. We will measure how far the observed counts are from the expected ones. Ultimately, we will base our decision on the size of the discrepancy between what we observe and what we would expect to observe if the null hypothesis were true. How are the expected counts calculated? If events A and B are independent, then the probability of A and B equals the probability of A times the probability of B. We use this rule for calculating expected counts one cell at a time. Applying the rule to the first top left cell, if driving drunk and gender were independent, then the probability of being drunk and male is equal to the probability of being drunk times the probability of being male. By dividing the counts in our table, we see that the probability of being drunk is equal to 93 divided by 619, and the probability of being male is 481 divided by 619. And so the probability of being drunk and male is 93 divided by 619 times 481 divided by 619. Therefore, since there are a total of 619 drivers, if drunk driving and gender were independent, the count of drunk male drivers that I would expect to see is the following, circled here in red. So the formula for calculating expected counts is column total times row total divided by table total. Following this formula, here are the complete tables of expected and observed counts. Importantly, the single number that summarizes the overall difference between observed and expected counts is the chi-square statistic, denoted as chi or x squared, which tells us in a standardized way how far what we observe, that is the data, is from what we would expect to observe if the null hypothesis were true. Here I show you the formula. For each cell, we take the observed count, subtract the expected count, and square that value. This value is then divided by the expected count, and then this number is summed for all of the cells in the table. Once the chi-square statistic has been calculated, we can get a feel for its size. Is there a relatively large difference between what we observe and what the null hypothesis claims, or a relatively small one? It turns out that for a 2-by-2 case like ours, we are inclined to call the chi-square statistic large if it is larger than 3.84. Therefore, our test statistic is not large, indicating that the data are not different enough from the null hypothesis for us to reject it. For other cases, other than a 2-by-2, there are different cutoffs for what is considered large, which are determined by the null distribution in that case. We are therefore going to rely only on the p-value to draw our conclusions. Even though we cannot really use the chi-square statistic, it was important to learn about it, since it encompasses the idea behind the test. The p-value for the chi-square test of independence is the probability of getting counts like those observed, assuming that the two variables are not related, which is what is claimed by the null hypothesis. The smaller the p-value, the more surprising it would be to get counts like we did if the null hypothesis were true. Technically, the p-value is the probability of observing a chi-square at least as large as the one observed. Using our statistical software, we'll find that the p-value for this test is 0.201. A p-value of 0.201 is not small at all. There is no compelling statistical evidence to reject the null hypothesis, and so we will continue to assume it may be true. Gender and drunk driving may be independent, and so the data suggests that a law that forbids sale of 3.2% beer to males and permits it to females is unwarranted. In fact, the Supreme Court, by a vote of 7-2 majority, struck down the Oklahoma law as discriminatory and unjustified.
Now that you have a feel for chi-square tests of independence, I'm going to use this tool to test the hypothesis that I had originally proposed. Specifically, is how often a person smokes related to nicotine dependency among current young adult smokers. Or, in hypothesis testing terms, is smoking frequency and nicotine dependence independent or dependent? That is, are the rates of nicotine dependence equal or not equal among individuals from my different smoking frequency categories? For this analysis, I'm going to use a categorical explanatory variable with 6 levels, the number of days smoked per month, which you may remember I call US freak mo, with the following categorical values: smoking approximately 1 day a month, 2.5 days a month, 5 days a month, 14 days a month, 22 a month, or 30 a month. My response variable is categorical with 2 levels, that is, the presence or absence of nicotine dependence, called tab12 MDX in the NESARC dataset. To produce a chi-square table in SPSS, we will go to Analyze, Descriptive Statistics, then Crosstabs. Choose tab12 MDX for the rows and US freak mo for the columns. Next, click Statistics and confirm that we want a chi-square test. Finally, click Cells. Here we can include both the observed values and the expected values, if we so choose, as well as row percentages, column percentages, and total percentages. Click OK. The SPSS results for chi-square include a table of the response variable by the explanatory variable, and also a calculation of the chi-square statistic along with the associated p-value. Looking back at our chi-square table, also known as a cross table or cross tabulation, you can see a myriad of numbers and percentages with such labels as frequency percent, row percent, and column percent. Although our p-value of 0.00 clearly tells us that smoking and nicotine dependence are associated, that is, they are not independent, actually trying to understand what that association is can be very confusing when examining a chi-square table. So before we try to interpret this output, let's look at 3 different tables that pull apart the different numbers represented in a cross table. Table A shows row percentages in that each cell includes a percentage of the observations within each row, i.e., the region. As you can see, adding across the rows gives us 100% of the observations within region. Table B includes the total percent of observations in each cell. The percentage of each row and column add up to 100% total. Finally, Table C shows column percentages. Each cell includes the percent of observations within a column, that is, within groups either insured or uninsured. Adding down the columns gives us 100% of observations by insurance status. Note that we are not interested in the column percentages for those observations without nicotine dependence, indicated by the dummy code of 0. Instead, we're interested in describing the presence of nicotine dependence within the smoking frequency groups, that is, these column percentages circled in red. If I use the SPSS legacy dialogues in graphs to graph the percent of young adult smokers with nicotine dependence within each of the smoking frequency categories, I could visualize the association and see that there seems to be a positive linear relationship. That is, the more days per month that a young adult smokes, the more likely that she or he is to have nicotine dependence. I know from looking at the significant p-value of 0.00 that I will reject the null hypothesis in favor of the alternate hypothesis that not all nicotine-dependent rates are equal among smoking frequency categories. If my explanatory variable had only 2 levels, I could interpret the 2 corresponding column percentages and be able to say which group had a significantly higher rate of nicotine dependence. But my explanatory variable had 6 categories, so I know that not all are equal, but I do not know which are different and which are not. As we saw with the f-test and p-value in the analysis of variance, when the explanatory variable has more than 2 levels, the chi-square statistic and associated p-values do not provide insight into why the null hypothesis can be rejected. It does not tell us in what way the rates of nicotine dependence are not equal across frequency categories. there are of course many ways for the rates to be unequal. Having each of them as unequal to one another is just one of them. Maybe there are only two of the population rates that are not equal to one another. To determine which groups are different from others, we will again need to perform a post hoc test by conducting post hoc test comparisons between pairs of rates in a way that avoids excessive type 1 error. In other words, we need to avoid rejecting the null hypothesis when the null hypothesis is true. I would really love to tell you that the post hoc pair comparison tests are as easy to conduct in the context of a chi-squared test of independence as they are in the context of an ANOVA. Unfortunately, though, the task is a bit more arduous. There is no built-in, follow-up multiple comparison test available for this procedure. If we reject the null hypothesis, we need to perform comparisons for each pair of nicotine dependence rates across the 6 smoking frequency categories. In the case of the 6 groups, we actually need to perform 15 pairwise comparisons. With these red brackets, I'm illustrating 8 of the 15 pair comparisons that we'll need to conduct. Here are the remaining 7. As you can see, there are so many that it's actually difficult to illustrate this graphically. If you'll recall, the family-wise error rate for 15 different comparisons is 0.54. This means that if we do not protect against type 1 error, we will be wrongly rejecting the null hypothesis and saying that there is an association over half of the time. This gives us about a 50-50 chance of being right, which would obviously give us absolutely no confidence in our decisions. So, to appropriately protect against type 1 error in the context of a chi-square test, we will need to use a post hoc approach known as the Bonferroni adjustment. The goal of using the Bonferroni adjustment is to control the family-wise error rate, also known as the maximum overall type 1 error rate, so that we can evaluate which pairs of nicotine dependence rates are different from one another. Briefly, the process would be to conduct each of the 15 paired comparisons, but rather than evaluating significance at a level of p of less than 0.05, we would adjust the p-value to make it more difficult to reject the null hypothesis. The adjusted p-value is calculated by dividing 0.05 by the number of comparisons that we plan to make. So if we make 3 comparisons, we would only reject the null hypothesis if the p-value were 0.017 or less. For 15 paired comparisons, our adjusted p-value is 0.003. So, adjusting the p-value is definitely the easy part of the process. Now for the more challenging part. For the actual post hoc testing, we need to run a chi-square test for each of the 15 paired comparisons. To do this, we will need to subset the data. If you'll recall from the earlier video, we will need to subset the data by selecting cases. Go to Data, select Cases. Click on If condition is satisfied. We will then need to specify the condition. Here I only want to compare US freak mo equaling 1 against equaling 2.5. In this command I am saying subset to only when US freak mo equals 1 or US freak mo equals 2.5. Hit continue, then OK. You'll see here that we've filtered to only those groups where US freak mo equals 1 or US freak mo equals 2.5. Now let's rerun our chi-square. I now get a chi-square table that includes only those 2 frequency groups by the presence or absence of nicotine dependence. Again, I want to focus here on the column percentages, 9.9 and 18.5. Are these 2 rates significantly different from one another? If I look down to my chi-square value and probability, I see that they aren't. So, I fail to reject the null hypothesis since the probability value is not less than 0.05. And it is definitely not less than the Bonferroni adjusted value of 0.003. This process will need to be repeated for all of the post hoc tests that we need to run. For example, for the next group, we'll go to Select Cases, and then change the if condition to the value 5. We will then rerun our chi-square. My goal is to examine the p-value for each of the paired comparisons and to use the adjusted Bonferroni p-value of 0.003 to evaluate significance. Here I have created a table that shows the p-value for each of the paired comparisons for my output. Obviously, there are several that are less than 0.003. As you can see, the smoking frequency group 30, that is, smoking 30 days in a usual month, is significantly different than each of the other smoking frequency levels. In addition, the smoking frequency group 1 has significantly different nicotine dependence rates than smoking frequencies group 14 and 22. Using the letter convention, in which nicotine dependence rates with the same letter are not significantly different, these post hoc findings can be pictured like this. Here is another way that we could picture the significant differences between rates. As you can see, the more differences there are, the more challenging this visualization can be to create. Again, I know that was a lot to absorb, so let me quickly summarize the chi-square test of independence for you. First, a chi-square test of independence is used when we have a categorical explanatory variable and a categorical response variable. The null hypothesis, that there is no relationship between the two categorical variables, they are independent. The alternate hypothesis is that there is a relationship between the two categorical variables, i.e., they are not independent. The chi-square statistic is calculated considering both the observed and expected counts on each of the table's cells. If your explanatory variable has more than 2 levels, you will also need to conduct a post hoc test. We will use the Bonferroni adjustment to protect against type 1 error, and then run the chi-square tests of independence for each of the paired comparisons. Now you are ready to test a categorical by categorical relationship. If your own research question is a quantitative to categorical relationship, I would like you to categorize the quantitative explanatory variable and test the association with the chi-square test of independence. Of course, the chi-square test is the goal of assignment 7. Good luck, and always ask for help when you need it.